Everyone. Up to now, we have discussed physics and mathematics. From now on, we are talking about statistics. And in statistics, we are going to start a new chapter, which is chapter number 3, bivariate distributions. Now, we will talk about uh, here, we will talk about these following topics. Now, you can see from the list of topics that this chapter is quite long. Okay, and I think this is the longest chapter in our book. So I will take time, and I'm not going to write everything, and I'm not going to explain everything, but I'm going to just explain overall picture and theory. And I'm pretty much not doing any kind of. I will do some important numericals, but I'm not going directly towards the numerical approach because it takes time, and these numericals in this question, the problems in this chapter are quite long as well to solve. So I'm not going towards that point. Okay. Now let's directly move into the video. Let's talk. So let's discuss about two-dimensional random variable. And for understanding that, let's take an example which has two variables. For example, uh, we take coin toss for 3 times as an example, is an experiment, and we get a random sample as this. Okay. Now, if we want to assign a single random variable, actually single two-dimensional random variable, let's say a random variable. If you want to assign a random variable to each of the outcome, what can you do? If you consider just a single variate random variable, then you would uh, make it as like 3. Okay, you can say it to be 3. Now, what about this? What is the random variable for this? Because we have two kind of variables there. We have two kind of variable there, so we cannot define a random variable that is only univariate. So we have to define a random variable that is two-dimensional. That means if you want to hold account of this, and then the random variable that you assign must has a value of 3 and 0. If okay, so we have considered x and y, right? It means we have to say 0 and 3, and again this is 1 and 2. Now this is a random variable. This kind of random variable, this kind of two-dimensional random variable, would account of both kind of variates in this random sample, okay, or the sample space. That means we have to get a two-dimensional random variable. Now let's say we have a random variable x and y, where x is a number of tails and y is a number of heads. And if we do so, we get that yes, it works because we have two kind of variates, and we have defined what these variates means. So this is what a two-dimensional random variable is. So to summarize the overall idea, what I can say that if we have an experiment and uh, we have got such kind of experiment where we can get two where we have two kind of variates, then we can use two-dimensional variable to hold account of both. Okay. Now let's go to the joint probability mass function or density function. Okay. So let's talk about bivariate probability distributions. And bivariate probability distribution means we have a probability distribution of two random variables. So if we consider the previous example of coin toss, then let's suppose we get a random variable xy equals 0 and 3. It means we got 3 heads, right? We get 3 heads and 0 tails, where x denotes the number of tails and y denotes the number of heads. If such things happen, then we can now, if we want to write the probability of happening of such kind of event in such kind of experiment, we need to define a quantity. We need to define a quantity to describe what the probability of any random variable is, any uh, random result is, right? So for that we need to define a density function. Now this is what the density function is. If we have a discrete distribution or discrete probability, discrete random variables, it means we have countable, we can say countable random variables. Then we can do that by using GPMF, that is joint probability mass function. Now the joint word joint here comes from the fact that these are two-dimensional. Okay, so we can say that to be two variates, and that's why we need two summations. That's why we can say it's a joint probability mass function. And joint probability mass function is used for discrete random variables, and this is defined by this: Pxiyi is equals to probability of x equals xi and y equals yj. And the math itself is talking that this mass function defines the probability of happening of such events, right? Now similarly, and there are some conditions to define this probability density function. And actually for mass function, that is, the condition must is that the probability of happening something must be zero or greater than zero. It means the probability cannot be negative. That's a known fact, and it accounts for that. And the second thing, the summation, that you can see the two summations. And two summations towards the fact that if we add all the probability, or the probability of all events happening, then it should not exceed one. Okay, it must exactly be one. That is what it says. So again, the same thing for continuous random variables. We get to use JPDF, that is joint probability density function. And density function is defined as an interval, so we don't say that x equals 3. We say x lies in between 3 and 5 in this way. Okay, if we do such interval wise calculation, we use joint probability density function, and there are the same conditions but in the different order. The first one says the same thing, the mass, the density function must be greater for any one or any of the probabilities. And the second integration sign means that the probability of all events must equals to 1. So this is it. This is what the probability mass and density function is. So let's talk about joint probability distribution function. As the name itself is quite clear that we are talking about the distribution here, it means we are talking about the value of a single random variable, and we are trying to find out uh, the probability up to that point. That means, let's suppose we want to find out the probability that x is always greater than or equals to 2, or y is always smaller than or equals to 3. So we are not defining a single value for the random variables. We are defining a limit. Okay. In such case, we have to consider all the other probabilities of other random outcomes. In such case, we can use something called joint probability distribution function, and this is defined right in this way. Okay. Now you should understand that the probability distribution always starts from the first value, and it goes in increasing fashion. You should understand that, and ultimately it becomes 1. That is the whole probability. So okay, you can understand it in the form of CF, cumulative frequency too. It just work as the CF but for the probability of the random variables. Okay, in this case we use the two variate random variable, or two dimensional random variable. Now so if it is a discrete, we use summation sign, and if it is a continuous random variable, then we use a integration sign. I don't think there's much to talk about, so let's go directly to the marginal distributions and conditional distributions. Okay, when the joint probability distribution of two random variables x and y is given, a situation may be arised where we need to determine the probability distribution of x alone or y alone from the given joint probability distribution, and then the probability distribution of only one random variable x or y is called marginal probability distribution of x or that of y. So you can see that there uh, px equals summation y pxy. Now here we have considered x to be common or x to have certain value, and we have just sum it, and we have just did the summation over y, right? That means here x is constant, so we are not talking about the value of x, and we are letting it be something, and we are just focusing on y, ignoring x. In a similar way, if we try to find the marginal probability of y, we will consider the x to be nothing. Okay, sorry, y to be nothing. It means we consider y to be some value or something, and we are just focusing on x, and we sum that x, and we get this equation. So it means if we have p of y here, it means we have the marginal distribution of y. It means y is taken constant, and x is summated over all of it. If we have marginal distribution or marginal probability of x, it means we have x is a constant, and we have to sum up to y. So this is what the concept of whole marginal distribution is. Yes. So now that was for the discrete case, and if we consider the continuous case, then we have this thing f of x equals integration minus infinity to infinity f x y dy, and f of y equals minus infinity to infinity f x y dx. Now one thing you should understand here is, and many students get confused here, including me, was how do we find which thing to so how do we define uh, to do integration in in which variable? It means what do we put here, dy or dx? So for that, let's see this one. We have to find out the marginal probability of x. It means we have to consider x to be constant. It means what is changing, dy. That's why dy. If we consider f of y, what is the marginal? So y is a so we have to find out the marginal distribution on the basis of y. It means we have to consider y to be constant. That means what is changing, x. That's what dx. This is it. Now I think you understand this relationship between the density function and the distribution function, and that is the density function is actually a derivative, a first derivative of the joint, sorry, not joint, but the distribution function. So density function is differentiation, first differentiation of distribution function itself. Okay, so this is something that you should know, and it would be very handy when we do some numericals. So this is it. This is about the marginal distribution for both discrete and continuous case. Now let's talk about something else. Okay, so let's talk about conditional distribution. Conditional distribution means the distribution of conditional probability. If you remember the formula, something called conditional probability, then you would understand, and you remember this formula where we discuss about the probability of something in relation to something. For example, if something happens, only something happens. So in this way, so if you have such kind of probability, then this is called the conditional probability. Now we are talking about the distribution of those kind of probabilities. Here we can see conditional probability mass function is given by in this way, where x equals x is this is the intersection sign, y equals y, given py equals y, where y equals y is greater than 0. Similar thing with the y, similar thing with the x2, and then the density function or the conditional density function, that means for the continuous variables, and it is given by this in this way. Now, if you want to find out the, okay, wait a second, it is not comma, it's a public sign, or we can say it to be uh, plus, okay, or given that it is red, given that, and statistics. Now in fy given fy, xy given fy, this is how we get the conditional probability density function, and this x given y is actually partial derivative of function, that is distribution function xy given x. So again, you can see here y is a probability distribution of x given y. So we use the differentiation of x right here. Just notice that. Okay, this is correct. And if we talk about distribution of y given x, then we talk and we write the partial derivative of y in the denominator. You can understand that, okay? So because we are trying to find out something on the basis of something, right? Now we cannot consider condition to be the initial or the original case. So the given y is a condition. That's why it cannot be considered as something fundamental or something uh, elementary. That's why we cannot use y. That's why instead of x, instead of y, we get x. Okay? I don't know how clear I am to explain this, but I'm trying my best. I hope you understand what I'm trying to say. So this is about the conditional distribution, and now we have to discuss a theorem which is defined on the similar topic, that is conditional distribution. And after that theorem, we will see this independence of random variables.